Okay, just taking a little length of time with me getting that up. Goodness me. Okay. Well, what we want to look at today is engineering science. And again, level 4, and this is outcome 4, tutorial 1. Now, you guys can't see what I'm looking at, but you need to look at the engineering science video, okay? And it will be clearly marked. You cannot miss it, okay? Outcome 4, tutorial 1, syllabus. Now, what we're looking at here is be able to apply single-phase AC theory to solve electrical and electronic engineering problems. AC electrical principles, features of AC, sinusoidal waveform, voltages, currents, explanation of how other more complex waveforms are produced from sinusoidal waveforms, RLC circuits, etc., etc., etc. Now let me just move in here so we can see this, hopefully. Okay, nope, it's giving me a lighting issue. Okay. Let me just try something here. I'm just going to see if I can make it a little bit bigger. No, I can't make it any bigger because it goes off screen then. And then that does not help me in the least. Okay. But we should be able to bring it up closer there, shouldn't we? Okay. Right. If you are not familiar with the basic theory of alternating electricity, electrostatics, and electromagnetics, you should study the prerequisite tutorials, okay? Now again, contents. Revision of basic AC theory, root mean square values, complex waveforms, fundamental frequency, harmonics, synthesizing complex waves, generation of harmonics, square waves, triangular waves. Now reactance and impedance. Now capacitive reactance XC, inductive reactance XL, and filters. Okay. Now this work is produced by a guy called DJ Dunn, and I thank him for his work basically. So, but in saying that, you cannot just go onto his website and do the work. It doesn't work like that because obviously he needs pain overall. Okay. So, but you can have the opportunity to print off certain works sheets. He has provided some answers, but you need to be aware that sometimes the answers are incorrect because the calculations, it's not his fault. So don't get me wrong. It's just that you get errors when you're doing bulk work, I should say. I know I've made errors myself, and you've probably seen them on my videos as well. So nothing big. Now here we have revision of basic AC theory. Students already familiar with basic AC theory should go straight to the next section. A pure alternating current or voltage varies with time sinusoidally as shown. It is possible to obtain AC with other graph shapes such as square or sawtooth. Okay? Okay. Couldn't reach it, but I was going to try for extra lighting. But let's see if this gives us what we want. Okay. Now, a pure alternating current or voltage varies with time, sinusoidally as shown. It is possible to obtain AC with other graph shapes such as square or sawtooth. Just recapping. And here you have your sinusoidal waveform, okay? You have your max, positive, negative half cycles, okay? Peak to peak values. And when you say peak to peak values, it means what it says, peak to peak values, okay? Your periodic time of one cycle, okay? Now again, you need to be looking at this in engineering science, okay? Engineering science. Now, what I'm surprised at here is that I didn't print this off. I'm just trying to figure out how I got this down here, but never mind. I'm going to continue and see how it comes out. If it doesn't, I'm not happy with it, then I'm going to have to remake it. Okay, the voltage or current changes from a maximum plus in one direction through 0 to a maximum minus in the other direction. This occurs at times at f times a second. F is the frequency in hertz. Okay, 1 hertz equals 1 cycle per second. The time it takes to complete one cycle is t seconds. The periodic time, it follows that t equals 1 over f. Let's just look at the waveform before I go up again, okay? Now the maximum value of volt or current is called a peak volt or current, and this is the amplitude of the waveform. The peak to peak value is double the amplitude as shown on the diagram. The arithmetic average of the volts and current over one cycle is 0. However, if AC is applied to an electric fire, for instance, electric energy is changed into heat on both the positive and negative halves of the cycle. So the electric power is not 0. If direct current had been used, the electric power would be calculated from EP equals volts times current. In the case of AC, clearly we cannot use average volts and currents to do these calculations, as the answer would always be 0 due to the rising and falling of the AC waveform. Root mean square values. Now that's values, okay? It's not vales. Values. Root mean square values. RMS. When you studied Ohm's law, you learned that electric power may also be calculated with the formulae EP equals I squared R, or EP electric power equals V squared over R. Now, okay, we'll leave that for a moment, EP electrical power, because I can see what he's trying to say, basically, but you have to make your own interpretation for yourselves and find your own learning style, for that matter, okay. These formulae work with positive or negative values, since a negative number is positive when squared, and power is always positive. In the case of AC, we must use the average value of V squared or I squared, and these are not 0. The diagram shows how a plot of V squared or I squared is always positive and has a mean height, okay? And again, as I said before, you need to be looking at engineering science for this video which I'm making now, okay? So here you have your mean height, okay? Voltage rising and falling. But what we're looking at is we're trying to find the value of the maximum height. So what we've done, we've taken samples of each of these from the right positive part of the cycle, okay? Now the mean height, then what we're going to try and do here, let me come back, we're going to try and find the mean height of the total area of this wave. I would say half wave actually, basically, but that's how I would look at it from my style of learning, Scully. Okay, right, the mean height, here we are. The mean height may be obtained by placing many vertical ordinates on it as shown, taking a graph of current with many ordinates, I1, I2, etc, etc, etc. Mean value, okay, this will be your formula here to apply, and that would be over n. Okay. So I'm just trying to see if this is going to be big enough on my screen, or do I need to do something else different? It's okay, I won't know till I come to play it back. If we take the square root of this, we have a value of current that can be used in the power formula. This is the root mean square, or RMS value. And here we have I RMS equals square root of your resultant values over n. It can be shown by the use of calculus that the RMS value of a sinusoidal waveform is 0.707 of the peak value. We use RMS values with AC so that we may treat calculations the same as for DC. When you use a voltmeter or ammeter with AC, the values indicated are RMS values. Okay. And here's your self-assessment work for you to do. Okay, the periodic time of an AC voltage is 0.002 seconds. Calculate a frequency, and we have the answer. Now here I've given you the answers, okay, or my associate, or I should say Mr. Dunn has. Okay, he's providing you with the answer, but that does not mean that you do not do the calculations. You need to know how they got these answers. Okay, that is for you to find out. Okay, and to make sure that you've applied the principle and the formulae to arrive at a given solution. Complex waveforms, fundamental frequency. A sinusoidal voltage or current is described by the mathematical formula V equals V sine omega t, or I equals I sine omega t. Omega is the angular frequency in radians and per second, and this is related to frequency f hertz by the formula omega equals 2 pi f. Now you need to be able to take down the information and the formulas for yourself and to know how to apply them. That is for you to do. And at this stage and level, you should be able to do this for yourself. Now, if you haven't or not able to, go back and look at your previous work. Okay. Again, here's our sinusoidal waveform or AC waveform, showing you the max and the peak-to-peak values. The sinusoidal voltage formula is then V equals V sine 2 pi ft. In this formula, f is the fundamental frequency. Look at harmonics. me just go back up a bit, make sure everybody can get this into play. Okay. Let's look at harmonics. A harmonic is a multiple of the fundamental frequency. 2F is the second harmonic, 3F is the third harmonic, NF is the nth harmonic, harmonics to any number, basically, okay? Synthesizing complex waveforms. Now here, that would be your normal waveform, AC. But by adding another waveform to it, we then begin to get this. Waveforms with shapes that are not sinusoidal may be synthesized from one common sinusoidal waveform. The proof of this is not given here, but the following is mathematically correct. This graph shows the result of adding the first and third harmonic with equal amplitude. Now the first and third harmonic with equal amplitude, okay? And here's where we are, okay? We're just beginning to create our harmonic situation. But in reality, the amplitude of the harmonic is likely to be less than the amplitude of the fundamental. This graph shows the effect of adding the third harmonic with a third of the amplitude. We will show that various waveforms can be produced by adding harmonics together in various ways. So what we're saying here is that from this simple waveform here and process, we can begin to generate, by adding other harmonics, we can almost begin to generate a square wave, if you like. And we can filter that and clean it up. And I think that comes up somewhere along the lines, okay? Now, generation of harmonics. Generation of harmonics. An ideal or linear amplifier produces a perfect replica of the input, but with greater amplitude as shown. Harmonics are generated when a sinusoidal signal passes through a nonlinear amplifier, and this amplifier could be something like an op amp. And here you have your input signal. It's amplified by here, then gets bigger. This then goes into here, if you like, and then it's added to this and becomes this. Now here you will notice that you've got some little dips here. Those need to be filtered out before you can utilize it as such. Okay. Square waves. It can be shown that if we add harmonics according to the formula below, we get a square wave form. Okay. Now here's the formula. I'm not going to read that out. That's for you to read out for yourselves. Yeah, you should be able to do that. It should be visible. Yeah. The formula is an infinite series. In reality, square waveforms are really DC levels that suddenly change from plus to minus. Okay, and that is what we can end up with when we generate a square wave. Triangular waves. It can be shown that if we add harmonics according to the formula below, we get a triangular waveform. The formula is an infinite series, and again similar to above. Okay. Note that in this series, a phase shift of pi radians is added to each. Reactance and impedance. Now I must admit, this has always interested me. Reactance and impedance. Capacitors and inductors have a property called reactance, denoted with an X. On their own, they may be used with a form of Ohm's law such that X equals V over I. Okay? Both V and I are RMS values. The value of X depends on the frequency of the AC, and this is why they are called reactive. It should be noted that a pure capacitor and inductor does not lose any energy. A resistor, on the other hand, produces resistance by dissipating energy, but the value of R does not change with frequency, so a resistor is a passive component. Sorry, I just got off, my camera just came offline there then, 1 second. Okay. When a circuit consists of resistance, capacitance and inductance, the overall impedance is denoted with a Z. The units of R, X and Z are ohms. Capacitive reactance XC. Now, when an alternating voltage is applied to a capacitor, the capacitor charges and discharges with each cycle. This means that alternating current flows in the circuit but not across the dielectric. If the frequency of the voltage is increased, the capacitor must charge and discharge more quickly, so the current must increase with the frequency. The RMS current is directly proportional to the RMS value, V, the capacitance C, and the frequency F. Hence, I RMS equals constant times V times C times the frequency. It follows that I RMS equals constant times V times F times C. Okay. Now, this formula here, the constant is 2 pi, so putting V over I equals XC equals 1 over 2 pi FC. Now, note that when F equals 0, Xc is infinite, and when F is very large, Xc tends to 0. This means that a pure capacitor presents a total barrier to DC, but the impedance to AC gets less and less as the frequency goes up. This makes it an ideal component for separating DC from AC. If we put in a combined AC plus DC signal as shown, we get out pure AC, but with a reduced amplitude depending on the reactance. And here's what we're saying. We put in the AC plus DC. It have a large amplitude here at this moment, but when it goes through the capacitor, the amplitude is reduced. So we can see the effect that a capacitor has on an input signal. Okay. Just recapping, okay. So everything can be seen on screen. Okay, let's just make sure we got that in place so nobody can feel left out. Okay. Okay. Now here we have some work examples. Now please do these work examples. It is detrimental that you understand the concept behind this. Work example number 1. 15 volts RMS applied across a capacitor of 4.7 microfarads. Remember that 4.7 microfarads is 10 to the minus 6. Calculate the RMS current when the frequency is 20 Hz, 200 Hz and 2000 Hz. Here is your solution. 20 Hz x c equals 1 over 2 pi fc. Put in your values. Okay? Confirm that the answer here is correct. Current RMS current V over XC equals 15 over 1693 equals 0.00886 amps. Okay. Make sure you calculate those values for yourself. I don't need to do anything further on that. That's a matter for you now to work out, okay? Do all of the criteria and all of the examples. Do not leave it out. Self-assessment, again there for you to do, okay? Inductive reactance. A back EMF produced by a varying current is E equals L di over dt rate of change, and an equal and opposite EMF or voltage is needed to make the current change in the circuit. In order to overcome the back EMF, a forward voltage equal and opposite is required. Hence, in order to produce alternating current, an alternating applied voltage is needed. It can be shown that the RMS voltage needed to produce an RMS current is directly proportional to the current, the inductance, and the frequency, so that V equals I 2 pi FL. Hence, V over I equals XL equals 2 pi FL in ohms. Note that the reactance is 0 when F equals 0 and approaches infinity when F is very large. This means that a pure inductor has no impedance to DC, but the impedance to AC increases directly proportional to frequency. This is the opposite effect to that of a capacitor, and an inductor may be used to reduce the AC component of a combined AC and DC signal as illustrated. So what we're looking at here is we're putting in the AC DC level, but using an inductor we get actually a lower output. The amplitude has moved from here to here. So you can see the effect that the inductor has. It actually reduces the input signal from its original state. Okay, that becomes this using our inductor. Okay. Okay. Now again, here we have some work examples. Do the work examples. Engineering science, okay? And just to read this out in full, 15 volt RMS applied across an inductance of 4 microhenries calculate the RMS current when the frequency is 200 Hertz, 200 kilohertz and 200 megahertz. And here's all results. Make sure you apply them and you understand the concept as to how to produce and calculate your relevant information. Right here we have a self-assessment. Calculate the RMS current in an inductor of 60 millihenries when 110 volts RMS is. Yes, millihenries. When 110 volt RMS is applied at 60 Hertz. Okay. Now, do not just read the answer off there. Prove that the answer is correct. Don't just take it off the board. It's not your answer. Okay. Prove the answer. Make sure you got the same answer. Filters. You have seen that capacitors and inductors produce reactance that varies with frequency. If we use a suitable circuit containing both, we can filter out unwanted components of mixed signals. The diagram shows a low and high pass filter. In order to understand such circuits thoroughly, we need to move on to the next tutorial and study phasor diagrams, but we'll do that another time. Okay, but for now, let's look at how this is. High frequencies go down to ground. So we have our inductor here. We have two capacitors. The two capacitors will short circuit all high frequency to ground. That maintains our low pass filter, and it will low pass filter at our given frequency. Right here, what happens here now? We have our capacitor in our circuit, but we have two inductors going down to ground. This shorts all low frequencies down to ground and only allowing high frequencies to pass through. Okay, so low frequencies goes to ground using our two inductors, and the capacitor allows that high frequencies to pass through. But you can see here the high frequencies goes down to ground using the inductor, and the inductor is allowed to pass low frequencies. Okay, these diagrams you should be drawing out for yourself. Okay, making that work relevant. Okay, again, you cannot see what I'm doing here, you guys, but go to engineering science, the video that I've made for this. Okay, right, thank you, and I hope you find this useful. Have a good day. Let me just make sure that I've got everything in view and that everyone has an opportunity to follow it up through if they wish to. Okay, all right, so just bear with me. All I'm doing now is just recapping, making sure that everything is on my camera. And again, thanks to Mr. DJ Dunn for his information. Thank you. Okay, excellent. Okay, thank you. Have a good day. Bye-bye.